Hi there, welcome to this lecture series on matrix algebra. Today we cover lecture 11. This is part 1. The topic of this lecture will be on the dimension of a vector space and related topics. So in part 1 we'll talk about coordinate systems, different bases, and then later we'll have some theories and theoretical results with proof and examples. Okay, let's get started. Let's recall some previously introduced concept, that is the basis of a vector space. So if you have a vector space capital V and you have a set of vectors v1, v2 and vn, so there are n of them, and we say that these vectors will be a basis of the vector space if the followings are true. So first, this set of vectors, they are linearly independent. Second, the span of these vectors is exactly the vector space V, which means every element in the vector space V could be expressed as a linear combination of the vector set. We also have the following theorem, that is, let's say you have a vector space and you have a set of vectors that is a basis for that space. And this is a basis if and only if every vector v in V can be written in a unique way as a linear combination, which is expressed here. So for every vector v here in particular, you will have a unique set of, we can call coefficients, these x's, x1, x2, and xn, that is related to that vector. Okay? So once a vector v is given, then this set of coefficients are also uniquely determined. So each vector is related to a set of coefficients, which means each set of coefficients uniquely determine a vector in the space. And therefore, we give them the name, the coordinates. So this set of coefficients are now called the coordinates of vectors v with respect to the given basis. One thing we need to be aware of is that if you are given different bases of a vector space, then you will have different coordinate system. Let's take a look graphically of the vector space in R2. There are different ways of finding the basis. So let's look at the one on the left, this graph here. Here we are using the unit vector E1 and E2 as the basis. Then this is just the regular two-dimensional coordinate system that we are used to. So any vector in it can be expressed as x1 E1 plus x2 E2, where x1 is the perpendicular projection of the vector here into the x1 axis, and then x2 will be the similar perpendicular projection into the x2 axis. Okay. Now let's consider a different set of bases. Let's say we have two vectors, v1 and v2, and they are linearly independent in R2, and therefore they can be used as the basis. Let's say graphically, just for illustration, let's say v1 is in this direction and v2 is in that direction. And then what does it mean if I give a coordinate? How do we find the vector that's associated with this coordinate? Well, so you have y1 times v1 plus y2 times v2, right? That will be the new vector. So how do you find this vector? Well, you would take y1, v1. That is, you multiply v1 with y1, so it's a scalar multiple, then you get a vector in the same direction. Let's say you end up here. And then you want to add on top another vector that's a scalar multiple of v2. So you'll be going in the direction that's parallel to the v2 direction, and the length here would exactly be the length of y2 times v2, so this way. So you can also go this first, then you think y2 v2 plus y1 v1. So basically is a parallelogram formed by these two vectors, and the other tip here will be the new element v. Okay, so the same point, let's say this point and this point, they are the same point actually, but then in these two different coordinate system, the coefficients, the coordinates x1, x2 would definitely be different from this y1, y2. So similarly, on the other hand, if you have different bases, you have different coordinate systems, then the element with the same coordinate would be very different. Let's take a look at these graphs here. So this is the system using E1 and E2, and that's the one that we're familiar with. And then we can take 1 unit and 1 unit and 1 unit in the E1 direction, and we can take 1 unit in the E2 direction. And then over here we can draw parallel lines parallel to the E2 direction, many of them, and then over here we can draw the parallel line to the E1 direction. So basically we make what's so-called a grid, right? Then the coordinate, if you have a coordinate 1, 1 in this system, that will be, you make 1 unit in the E1 direction, and then you take 1 unit in the E2 direction. It will be here. It will be just the intersection of these grid points. And then, for example, here will be 2, 0, and then here would be 1, 2, 3 for the first element, and then 1, 2, 3, and 2. That will be the coordinate for that point. And then in a different basis, different coordinate system, for example here, if you use v1 and v2, and how do you form the grid? Well, it's a similar idea, except that now you have to take parallel lines parallel to the basis. So we have first this line through the origin, and then you can have 1 unit on that, and then you do the second through origin in the direction of v2, and then you find length of 1 in this direction, and then here then you can draw parallel lines to v2. You can have a bunch of them, and then for points on this v2 kind of axis, and then you can draw parallel lines with v1. Okay, so then you get this kind of a slanted grid, and then at every intersection, that will be the coordinate. So this one would be, you moved 1 unit in v1 and then 1 unit in v2, so that's 1, 1, and this will be 1, 2, 1 unit in v1, 2 units in v2, and so on and so forth. And so you see that the points with the same coordinate, let's say 2, 0 here and 2, 0 here, they are actually very different points, so they are different vectors. We now state a theorem regarding the dimension of a vector space. So if you have a vector space V and you find a basis v1, v2 to vm, there are m elements, and then you find another one which is a basis, so w1, w2 and wn, n elements. If they are if these two are bases of a same vector space, then the number of vectors in each must be the same. So m must equal n. So, in other words, all bases of the same vector space will have the same number of elements. Therefore, the number of elements is kind of a property of this vector space, and it is an important one. And therefore, we give a name, and we call this number the dimension of that vector space. Now, let's do a quick review of some related concepts we have learned in linear systems, which will be useful here. Okay, so the first one is that if you have a system of m equations and with n variables, then they can be written in this form: a matrix A times the unknown x equal B. And here the matrix A will have dimension m times n, and x is a vector of length n, so it's n times 1. And B is a vector of length m, so it's m times 1. So we have seen in previous discussion that in the case when n is bigger than m, meaning the number of variables is bigger than the number of equations, in that case there still might be no solutions. So a quick example will be this: x1 plus x2 plus x3 is 1, and the second equation is 2 times each add up to be 0. Then the second equation can be simplified into x1 plus x2 plus x3 is 0. And then you want 1 equals 0, which is impossible. So there are no solutions. Okay, so in this situation where it has no solution would always occur where the right-hand side vector is not a 0 vector. There are some elements here that are non-zero. And if the right-hand side vector is 0, then any system Ax equals 0 will always have at least one solution, that is, all the xi's, all the coefficients are 0. So A times a 0 vector will give you a 0 vector. So a linear system with the 0 on the right-hand side like that is a special one. And we actually give it a name, and this is called a homogeneous equation. And they are very much studied. Okay, so let's see a lemma first. If now n is bigger than m, this means the number of variables, which n, is strictly bigger than the number of equations, which is m. So in that case, if we consider what we call the homogeneous linear equation, the system Ax equal 0, then this one will have infinitely many solutions. Note that this does not contradict the counterexample we had in the previous slide, where we have a non-homogeneous system where the right-hand side B is not completely 0. Okay, in that case, it's a different discussion. Okay, let's see if we can give a intuitive kind of a proof or argument for this lemma. So when we solve this linear system, we will put the matrix in reduced row form. So let's say we have done that. Then, for example, it takes this form, and we can write out the coefficient matrix. And this is the A, and this is the right-hand side B. And then we can mark the leading entrance in blocks. That's what we have done, right? Once we're at this stage, then we will write out the solution. So in the solution step, we would look for columns that does not have a leading entry. So, for example, in this example, this row 2 doesn't have a leading entry. And then we will say that the solution x2 here will be arbitrary. And the solution for the other ones, you will solve them following the backward substitution procedure, which means they're not arbitrary. They'll be uniquely determined. It could contain the arbitrary x2 in the solution, but it's contained in a determined way. So, for example, here you will have x4 must be 0, and then x3 must be 0, x2 is arbitrary, and then x1, so here x1, these two are 0, x2 is arbitrary, let's say is c, and then x1 will be -3 times c, and that's your solution. Okay, so if the number of unknowns are greater than the number of the equations, and then we know that there has to be some number of columns that do not have a leading entry, because a leading entry, you have to have a reduced row form, and the maximum number of leading entries you can have is the number of rows. Okay, so therefore it's an argument for that lemma. Okay, so now let's go back to the theorem and trying to prove it. So remember the theorem? It says that if I have two sets of vectors, they are two different bases of a vector space, of the same vector space, then m must equal to n. So the number of vectors must be the same, meaning the vector space will always have just a fixed dimension, no matter how you try to represent it. Okay, so let's prove by contradiction. We have been doing contradiction. So let's assume the opposite. Let's say the m and the n are not the same. Okay, so we can just assume one is smaller. So let's say, for example, m is strictly less than n. Okay, and in that case, we will show that the vectors here, they become linearly dependent, and therefore it cannot be a basis, and that is a contradiction to the original assumption in the theorem. Okay, so since now the V is a basis, then span of this set of vector is equal to the vector space. And then all the W's are in the vector space. Therefore, each of these W's can be written as a unique linear combination. So let's write them. Let's say the coefficient is A11, A12, A1. And for the W1 and W2, let's call it A21, A22, and then so on and so forth, and the last one, Wn, will be An1, An22, Anm. Okay? Now, to show that the set W1 to Wn are linearly dependent, then we must find a linear combination, some coefficients x1, x2 to xn, such that this linear combination equals 0, and all the coefficients x1, x2, and xn, they are not all 0. Okay, so let's look into detail of this expression here. So on the previous page, we have written expressions for W1 and W2 and Wn, and we're going to plug them in. Okay, so they should equal to 0. Let's start with 0 equal. So x1 times W1. So we fill in the W1 from the previous page. So x1 times W1. And now the second line is x2 times W2. And that is the expression for W2. And so on and so forth. And the last one is xn times Wn. Okay, and then we can do distribution. We can distribute each of these xi's onto each term. So you will basically have x1 will be multiplying by each of these terms, and x2 will be multiplied on each of these terms, and so on and so forth. So what we want to do next will be rearranging these terms. So we see that kind of if you look at this kind of a column, I lined them up on purpose. So you see these, they carry a common factor v1. Then I can group this together and then take out the v1. And then the second column will be v2 can be taken out, and so on and so forth. And then the last one will be grouped together, taking out vm. Okay, so after rearranging terms like that, and then we can rewrite it. So summing up the first column, we'll have a v1 here, and we'll have summation of all these coefficients, the products of it. Okay, and then the second column here, we'll have v2 as a common factor taken out, and then you'll be summing up the coefficient, which will be x1 times a12, x2 times a22, to xn times an2. And you do that for all the columns, so on and so forth, and then all the way to the last one, which you have vm outside, and then adding up all the coefficients. And then remember, all that expression must equal to the 0 element. So what does that mean? Well, and remember, v1, v2, vm forms the basis of the vector space. So therefore, it's a set of linearly independent vectors. And then the 0 vector, the 0 element in the space, will have a unique representation, which means all the coefficients must be identically 0. Therefore, we'll have all these coefficients must be 0. Okay, so what do we have now? Okay, so now we have these, we collect all these constraints. Each coefficient must be 0, and then we see that we actually have m equations, and then we have n variables, x1, x2, all the way to xn. So, and then right hand side is 0, so this is a homogeneous system. Now, this is an excellent place to use our lemma, because we know now that m is less than n, and it's a homogeneous system. And our lemma tells me that there are infinitely many solutions. So, therefore, there must be at least one non-trivial solution. Non-trivial means not all the elements are 0. Because 0 is trivial, that one always holds, right? So there exist solutions where these coefficients are not all 0. And therefore we reached the contradiction and we proved our theorem. Okay, I hope that proof is okay. We will stop here for this part 1 of the lecture, and we'll continue our study in the second half. Okay, so hope you enjoyed this one. I'll see you soon.